Hello, my name is Eric, and I'm going to be talking about my SENG 475 project, which was a simulation of a double pendulum. Now, as you might imagine, a double pendulum is just one pendulum with another attached onto the end of it, as you can see in the figure on the right. Now, this is kind of interesting because it's chaotic, which means the initial conditions of it, even if they're slightly different, it'll drastically change the overall result. And currently, at least, I don't know if there ever will be, there's no equation that you can just punch in the time and get the current state of it. You need to sort of fully simulate it up to that point. Now, for this project, I'm going to assume the rods have no mass, and the mass is on the pendulums, they're just points. I'm also not going to have any drag, although I do use a bit of dampening just to make the simulation a bit more interesting and run smoother. Onto the implementation, I've thrown a bunch of math up onto the screen. This is all from Eric Newman's double pendulum page, which was very helpful. So yeah, essentially you can derive some pretty easy equations for the positions of the points. Take a couple derivatives, you got the accelerations. You can also figure out the forces acting on each of them. And through a bunch of substitutions and multiplications, you can get this kind of ugly motion of a double pendulum equation for each of the two angles. These are the angular accelerations. And yeah, that's pretty much all you need to get started. It's quite ugly math. For the actual technical details, I just used the provided Fedora virtual machine, as I'm sure everyone is. And yeah, I used OpenGL for my graphics. Now, this is actually the math right there at the top. It's not pretty, but it works. And yeah, so initially when I was researching for this project, I was looking into the Runge-Kutta method, or whatever that's said, which lets you perform several approximations, and you can sort of use a weighted average of those to achieve more accurate simulation. I thought that was absolutely necessary to even get a value. But as you can see up top, I actually am able to compute some accelerations, and I was actually quite happy with how that turned out. So I didn't fully go for the full accuracy, but I still think it turned out very well. Now, as for running the simulation, you can provide some pendulum lengths, the masses of the two pendulums, and then the initial angles of the rods. I provided a sample command there. There's also a demo, which has some commands filled in already. And yeah, one thing I'll mention, as you can see in the screenshot on the bottom right, the size of the points depends on the mass, just to make it easier to visualize. Now I'm going to switch over to the actual simulation. All right, so I've just got a command saved, and I haven't. This isn't actually from the install. This is just a build folder I have. I'm going to run it, and there we go. Now this is running pretty smooth on here. When I've run it from the UVix server through like an X11 forwarding, it's a bit slower. I wasn't a huge fan of the OpenGL loop that it forced me to set up using its built-in timers. I would have preferred a bit more control there. But I think it gets the point across. And yeah, it is quite chaotic, even if this is only an approximation. So yeah, I'm pretty happy with it. I'll let it play out for a bit longer, but thank you for watching the video, and that's about it. Thanks.